Like Pat said, I'll be talking about optimization and characterization of organic or carbon-based solar cells. I did this research over the summer at the University of South Florida with Evan LaFalce, soon to be PhD Evan LaFalce, Dr. Xiaomei Zhang, with my advisors Pat Pauly and Paul Stanley. So I did this research at the University of South Florida. Really beautiful there. I really like the palm trees. Thanks to the National Science Foundation's Research Experience for Undergraduates REU grant that allowed me to go there and do research for 2 months over the summer. So as a background, kind of looking at the big picture to start, solar power is a pretty viable alternative energy. It's kind of, some would say kind of a basic way of getting power. The way that it works, put simply, you get photons in from the sun and you get electrons out. So photons come in from the sun, you excite something and you extract electrons, which you can then use to power, power lights, power cars, power anything. Currently, the industry leader in solar power is silicon. That's what the vast majority of the solar panels that you see are made of, the huge crystalline sheets. They operate at about 25% efficiency, so 25% of the power that comes in from the photons from the sun, you're able to get out in usable electronic power. However, there's some difficulties that come along with this. You have a very high temperature of production. As silicon is made is very crystallized, you have to heat it up a lot to be able to get into the sheets that you want. You have to do a lot of the production in high vacuum and in a clean room. So this is an example of a silicon solar cell production facility. A lot more intense than the place that I was working in this summer, and I'm glad I never had to walk into a clean room like that. Also, it's difficult to change the shape. As you'll see in the next slide, a cool thing about carbon-based or organic solar cells is that they're flexible. You definitely wouldn't be able to make a silicon solar cell flexible. So kind of the movement to organic, in the last 10 to 15 years, organic semiconductors have really taken off. A lot of applied physics or chemical engineering programs have some sort of organic semiconductor research, and a lot of them is directly into these organic photovoltaics or OPVs, which these are. It's easier and cheaper production. All I did this summer was pretty much pipette things from one solution tube and drop it onto a glass substrate over and over and over and over again. And so, it took me 3 or 4 days to know how to do the production, and then from there I was pretty much doing it by myself without any supervision and pretty easy. While the organic solar cells have lower efficiency, they operate at about, the averages now are about 4 to 5%. The max is about 12.5 compared to the 25% efficiency from silicon. You get more watts per dollar out. So the cost efficiency of these solar cells is much, much higher than silicon because they're so cheap and so easy to produce. It's a fast-growing field. There's huge companies who are investing a lot of money to fund this. Actually made by the company who funded my research, or funded the lab that I was working in this summer. You can create they're envisioning creating giant rolls of these flexible solar cells that you can just roll on windows. They're talking about optimizing some of the energy levels, so you can roll them indoors, so you can, generate power just from kind of the ambient light inside. So while you're using it, you also generate some, which is pretty cool. And Dr. Zhang is one of the leading researchers in this field. She actually gave a TED Talk in Tampa a couple of years ago about this, which is pretty cool. So as a quick background to how organic solar cells work, I'll have a nice little nifty animation for you guys. So this is a solar cell. I'll go more into the layers and the production of this in a little bit. But we have a photocathode in indium tungsten and a photoanode in aluminum, a whole transport layer in PDOT, which I'll go into in a little bit. It's got a really long chemical name, and a electron transport layer in lithium fluoride, along with the active or charge generation layer in the middle, which is a mix of P3HT and PCBM. Again, really long chemical names that you guys will see in a bit. So kind of in a simplistic view, you have an electron hanging out in the highest occupied molecular orbital HOMO of P3HT. For you physics people out there, this is the valence band of P3HT. There's lots of electrons there. It's just kind of chilling. And then you get an incident photon that comes in hits the electron, gives it more energy, and excites it into the lowest unoccupied molecular orbital, LUMO, of P3HT, or the conduction band that allows the electron to travel across the P3HT. While this negatively charged electron is excited from the HOMO to the LUMO, we get a positively charged region called a hole that we can think of as a particle in the HOMO of P3HT. This electron hole duo is called an exciton. What we want to do is move the holes out up the energy levels and move the electrons out down the energy levels. So this happens at the interface between P3HT and PCBM in the active layer. The cell or the electron holes dissociate there, so they get far enough away that there's no attraction, no Coulombic attraction between them, and then we're able to extract the charges to the anodes, and running a current through this cell, we're able to extract the charge and generate power, which is essentially what we want. So this cell is called a bulk heterojunction cell. Bulk because you can think of it as a three-dimensional cell rather than two-dimensional film or a one-dimensional line. It's heterojunction because there are two or multiple parts in the charge generation layer. There's the P3HT and the PCBM. We call it you kind of think of it as a sandwich model. So you have, as it was described to me the first day of my job over the summer, you have the photocathode and the photoanode as the pieces of bread. The charge generation layer is the meat, and then you have your tomatoes, your lettuce, and in my case, lots and lots of ketchup. So a really cool thing about this is it's solution-based processing. So like I said, the vast majority of this is all pipetting things from one tube and putting it onto a glass substrate, again, over and over and over. So there's lots of cool things that could go into this. We have novel materials and fabrication techniques. So we worked with actually Dr. Zhang's husband at Utah State. And he's a chemical engineer, and he would give us new chemicals to try out in the charge and electron transport layers, which was pretty cool. And he's coming up with those, every couple months. There's also some new fabrication techniques. There's an artist who used to work in my lab. He was a professional artist before he decided to go and get his PhD in physics. Go figure. And he had this spray painter that we would use to put on some of the layers, which was pretty cool to see. He was actually the pioneer of that, which has now kind of started to branch out to other labs. And kind of the bottom line is that this is new and exciting physics. I mean, stuff that I would have seen in the classroom. These organic semiconductors are pretty cool. And I mean, stuff that I'd hope to continue in grad school. So for device fabrication, as a brief overview, it's a 24-hour multi-step process. Like I said before, it's simple and inexpensive. I did all of the work in a single lab at the University of South Florida. Most of it was done in a glove box. So any of you guys who have ever worked in a glove box know that it sometimes gets a little sticky in the gloves. But besides that, there are pretty much no problems. It's easily manipulated. You can change things at pretty much any stage in the production process. The one drawback is that it's fairly volatile. So you can produce two cells exactly the same at exactly the same time, and one of them can work beautifully and one of them cannot work at all. So it's also pretty frustrating. So as a brief overview, you start with a 1-inch by 1-inch glass substrate. On top of that, you put indium tinoxide. I was not involved in this step. That was Evan who did that because he had to do it in the clean room. On top of that, you spin coat PDOT. On top of the PDOT, you spin coat the active layer, and then you thermal vapor deposit your electron transport interfacial layer and your photocathode on top, and that gives you this sandwich model. So starting with ITO on glass, again, this was not a step that I was involved in. You etch it using photolithography and photoresist in the clean room. The one thing that, or one of the big things that people are trying to do in organic solar cells is move away from using ITO as the final hole acceptor. It's expensive, it's inorganic, and this is the most expensive technique that we have in this. So they want to move away from using ITO. However, it's very it has a high electrical conductivity and it's transparent, which is what we want. So we're trying to find other ways of having something that has high electrical conductivity and transparency that's a little bit more inexpensive to produce. So after that, this is where I come in. I start with PDOT PSS, or poly 3,4-ethylene dioxythiophene. So that's why I don't say that every time, and I just say PDOT. That's the chemical structure of it. I spin coat it at 5,500 RPM. So this is the spin coater. You put the 1-inch by 1-inch glass substrate right there, and then this is all in the glove box, and then you turn it on, and it spins really, really fast at 5,500 RPM to produce about a 35 nanometer layer. And then I bake this at 30 minutes at 120 degrees C to get out all the water and just have a layer of PDOT. Next, I move towards the active layer or the charge generation layer. This is a PCBM and P3HT mix at a 1-to-1 mass ratio. PCBM is pretty cool. I see George in the back. I know he loves the buckyball. And so it's pretty much a buckyball or C60 with a functional group up top. The buckyball acts really well as has really good electrical conductivity, and this functional group makes it so you can dissolve it in solution. So we spin coat this active layer mix anywhere from 700 to 1500 RPM for 30 seconds. This produces a 75 to 150 nanometer layer. This is one of the things that we did vary, and then we let it dry overnight. And then the next morning, we come in and start our lithium fluoride and aluminum thermal vapor deposition. So what the thermal vapor deposition is you put crystals of lithium fluoride or kind of chunks of aluminum into a tray. You run current through them, it heats it up, and then you have the substrate up here, and the particles that are heated up go up and land on the substrate. A problem with this is that you get a lot of waste because you're only getting a tiny bit onto the substrate from what you want, but it's pretty easy. You can very easily control the layer thickness. We left aluminum at 100 nanometers, and when we used lithium fluoride, we had it at 6 angstroms, which is a matter of a couple of atoms thick. So you can control this very, very well. We are not 100% sure that we got 6 angstroms, but by the fact that lithium fluoride acts primarily as an insulator at thicker thicknesses, the fact that using lithium fluoride vastly improved our device performance indicates that we were actually able to control it to about 6 angstroms, which is pretty impressive. That's really, really small. And then the aluminum acts as our photocathode, so the final electron acceptor. So those were the conventional cells. So those are how kind of we started using it, using ITO as a whole transport. However, recent research into this has focused on an inverted structure. So using ITO as part of the electron transport, indium tinoxide as the electron transport, rather than ITO as the whole transport. So you switch the polarity of the cell. One thing is that this has increased stability in air over time. A problem with the conventional cells is that they decay pretty rapidly when you expose them to air. That's why all the production is done in the glove box. When I was testing some of the conventional cells, we had our testing outside of the glove box, just in the ambient air in the lab, and I could test it right out of the glove box. The glove box, by the way, is nitrogen rich. It's over 99.9% nitrogen. And so I could take it out of the glove box, test it in the air, wait 10 minutes and test it again, and it may not work. It decays that quickly. The inverted structures have a little bit longer. Generally, they still work after about 30 minutes, although it doesn't. Although that isn't good, it's still better than the less than 10 minutes that you get with the conventional cells. People have gotten higher efficiencies. We were not able to do that, but the 12.5% solar cell was used using kind of a quasi-inverted structure. Again, it's similar device architecture, so I won't go into the making of it. You have ITO, you spin coat zinc oxide, and then the active layer. And then we have a couple different deposition techniques with vanadium oxide, V2O5, and PDOT. We have thermal vapor deposition, and then we also have the spray coating that I talked about. And then on top, we have the photoanode in silver or gold. So just as a quick review of what I did when I was controlling the solar cells, I looked at differences in layer thicknesses. So the active layer, this charge generation layer of P3HT and PCBM, I varied from about 75 nanometers to 150 nanometers. And then with the zinc oxide layer in the inverted cells, again, I varied about the same from 75 nanometers to 150 nanometers by varying the spin rate. Again, the slower the spin rate, the thicker the layer. If you have a really fast spin rate, you have a thin layer. Additionally, I looked at the layer composition, so addition of interfacial layers. So these are the charge and electron transport layers on either side of the active layer. So we looked at the addition of lithium fluoride, and then the addition of vanadium oxide or PDOT and differences between the two. So next we go on to how we characterize these cells, how we analyze this data. So you can, while the solar cell is far from a perfect cell, or far from a perfect circuit, you can approximate it by by a circuit with 4 perfect components. You have a light source, or you have a current source, which is the sun, or in our case, the lamp. You have a diode that acts as a part that acts as a diode in the dark. A diode is something that only allows current in one direction, so current can only flow forward, it can't flow back. And then we have a shunt resistance and a series resistance. So we get 2 values right off the bat. We get current and voltage, or the short circuit current and the open circuit voltage. From here we can obtain the fill factor, which I'll talk about in a bit, and the efficiency, which is kind of the main thing of what we want. And then I'll look at how to calculate the shunt and the series resistance and how to optimize them. So the way that we look at these cells is through a voltage current curve in the light. I is current, V is voltage. We vary the voltage and see what current we get out of it. There's 2 kind of components of this that we want to look at. We have the open circuit voltage, which is where the external field matches the internal field, and we have no current. And then we also look at the short circuit current when we have no applied voltage, and just able to get out the current that the sun is providing, or in our case, the lamp. Excuse me. So looking at this, at the open circuit voltage and the short circuit current for conventional cells, we see that the 700 RPM with lithium fluoride, so with the added electron transport layer, at 700 RPM is about 100 nanometers thickness. We get kind of the best average of the open circuit voltage and the short circuit current. We see that 1000 RPM works pretty well without the lithium fluoride, and then everything else is pretty much up and down. Again, I mentioned this is really volatile. When we start testing them, we have no idea how well these cells are going to do. So when I got this data, it was as much a surprise to me as a surprise to everybody else in the lab. This is pretty much supported by the literature. They don't have an optimal charge generation layer, so 100 nanometers hasn't really been set as the optimum, although for the production that we were doing, we found that 100 nanometers was the optimal thickness. So next, we wanted to look at the fill factor and the efficiency. So the max power that we get out, P equals IV, so power equals current times voltage. And so the max power is when the current multiplied by the voltage is the greatest. The fill factor is taking the current that the max power is at and multiplying it by the voltage that it's at and dividing it by the open circuit voltage times the short circuit current. This gives us a way to kind of quantify at the kind of internal efficiency that the cell is working at. So how well is it performing in relation to how well it can perform. So good fill factors are at about 50%. So the ratio of this area, this green box, to the red box is about 0.5. With bad cells, it's less than a quarter, and there were a couple cells that I got that were about 0.6 to 0.65, which is pretty good. But kind of the bottom line is the max power that we get the efficiency out of. So all of these cells were looked at under 0.004 watts per centimeter squared, and so we looked at the power that we got, divided it by that, and got efficiencies. So for the fill factor and efficiency graph, again, we see that the 700 RPM, so 1000 nanometer thickness of the active layer with lithium fluoride gives us the best cells. That was kind of what we thought we were going to get by looking at the short circuit current and open circuit voltage on the previous graph, and everything else kind of falls off. The 1000 RPM looks pretty good, and then everything else is pretty bad. And then move into the inverted cells. Changing the electron interfacial layer, so electron transport interfacial layer, so looking at using vanadium oxide, PDOT, or nothing. We see that using PDOT works the best in here. Vanadium oxide doesn't really improve it at all, and using the 2 controls, which are the gold photoanode or the silver photoanode, don't really do anything. The problem with PDOT, however, is that you have to, when you spray it, you have to put it on something that maintains about 95 to 100 degree Celsius pretty continuously. We had a pretty inexpensive hot plate in our lab that did this, and for any of you guys who ever used hot plates, you know that they don't heat very uniformly anywhere. So we could have one in the center of the hot plate and one, an inch to the left, and there could be a 20-degree difference between the two. So that makes it really difficult to spray coat PDOT, and a lot of the PDOT cells that we used didn't work well at all. So we only got a couple to work. So then looking at the zinc oxide spin rate, so the thickness of this, of this electron transport layer, we see that 1500 RPM does the best. That's about 100 nanometers, and then 2500 and 3000 RPM don't produce well enough to work. They're not thick enough to be able to act as a step down for this electron. So the other way that we looked at these cells was under dark conditions. We didn't have a light on it. Under dark conditions, we only have a diode when we're running something from the running current through. So excuse me. So a diode is something, like I said, that current only flows in one direction. So it doesn't flow when voltage is negative, and we want it to flow a lot when the voltage is positive. The way that we find these resistances, we look at the shunt resistance as the inverse of the slope as V equals 0, and the series resistance as the inverse of the slope as V goes up. And again, we want a very high shunt resistance and a very low series resistance so we can get as much current through here as possible. So when we look at the varied interfacial layers, we find that the ones that work the best, which is the PDOT, we have the highest shunt and the lowest series, and with the other two, we don't have this duo right here. We have a high shunt and a high series, and then a high series and a low shunt, which is not at all what we want. When we look at the varied zinc oxide thicknesses, we see the same thing. The efficiency is hiding behind this guy right here. So we have a high shunt and a low series at 1500 RPM. We have a low shunt and a low series at 2500, and a low shunt and a high series at 3000. So again, 1500 is what we want, also characterized by by these resistances. So as a summary, we find that the active layer is optimized at 100 nanometers. This lowers the series resistance. We want to generate as much charge as we can. However, the thicker we have it, the more resistance you have, the more that the electrons and holes combine, and you can't extract the charge. We find that zinc oxide is optimized the most at 100 nanometers. This prevents reverse current, so it prevents current flowing in the reverse direction because it's thick enough that it doesn't allow for this leakage current. We find that adding interfacial layers helps a whole lot, so adding lithium fluoride and adding PDOT improves the efficiencies of the cells greatly, and also that we need this high shunt and this low series to have series resistances to have successful cells. So for future works, we want to optimize this PDOT deposition. So as I said, it doesn't do very well when you just kind of spray coat it on there. We want to find better ways of getting this PDOT on there because it does work so well. It's just very difficult to do. We also want to optimize the vanadium oxide thermal vapor deposit. It does, for whatever reason, it didn't deposit at very controlled thicknesses. So we want to kind of find out what's going on with that. We want to look at new materials, so look at some of the new chemicals that are coming out for some of these interfacial and charge generation layers. And also, something that I'm interested in, one of the researchers at Penn State, where I'll be going next year for grad school, is doing this thing on block copolymers. So making polymers that are, you have a whole layer and an electron layer kind of grouped together like that. You excite it in the charge generation layer in the hole. They associate at the interfaces, and then the electrons are free to just kind of move up, and the holes are free to just kind of move down, and it's a lot easier extraction with a lot less charge carrier recombination. So I'd like to thank my advisor, Pat Pauley. Paul Stanley's helped a lot. Major Jaffet was kind of the person who encouraged me to go into chemistry. I'd like to thank Rama in the back. He's worked with me a lot. Dr. Zhang and Evan at the University of South Florida. The Beloit College Departments of Physics and Astronomy and Chemistry, who I've taken a lot of classes with. Student Symposium 2014, and the NSF grant that allowed me to do this research. Thank you.